So in honor of Valentine's Day, I decided to give Jim's lecture for him today. So, I'm going to be talking about UPC, which is a project that I've been working on for a number of years, I think about 15 or so. And I'm going to talk a little bit more generally about even PGAS languages, partition global address-based languages that have been around even longer. But first, just a little bit about what I do in one short job advertisement. So in addition to being a professor here in computer science, I'm also the Associate Lab Director for Computing Sciences up at Berkeley Lab. This is where the NERSC facility is, although it's not technically up the hill. It's out in Oakland. And the ESNet facility, which is a wide area network that Berkeley runs for the Department of Energy to send large data sets around. And then the Computational Research Division, where there are people doing applied math, computer science research, and computational sciences, so applying computational techniques to a number of other science disciplines like cosmology and material science and climate change and things like that. So lots of opportunities. If you're interested in summer internships and things, let me know. And there are also a lot of joint projects and things like that at the lab. So that's my day job, I guess, right now, and I sometimes moonlight doing a little bit of lecturing still in classes. I'm going to talk today about this class of languages, and I know you have not even really started writing parallel code in the homework assignments yet, right? You're working on the homework one, the cache optimization one. At the very end, if you stay to the very end, you get to hear some hints about how to do homework one that David will give. Before that, I want you to think about, you've heard a little bit about shared memory programming, you've heard a little bit about message passing programming, MPI, kind of send and receive style programming, and I want you to think about this little programming problem, which is you're trying to kind of histogram something. So you're trying to count the number of instances of words with some different characteristics. Now, just to make it really simple, we'll just say we want to count the number of words that have that start with A, that start with B, that start with C, and so on. But in practice, we would have a much more interesting thing that we're probably histogramming, and also a much larger histogram than just 26 different counts. But we have a large stream of words that are coming at us, and we're trying to then count the number of them that are in each one of these buckets. And there's a number of different ways that we can try to do this. But let's say that you have a shared memory machine. And this is the kind of thing that people like shared memory machines for. It comes up in computational biology problems and other places where you have this kind of very irregular access pattern where you want to go and do these updates kind of irregularly across the machine. But so how would we do this in shared memory? We would just allocate an array, let's say, and would have each processor work on a subset of the stream. So somehow the stream gets chopped up into p different pieces, and each one of them is going to update the appropriate count whenever they see a word that matches that particular the value that has a letter that starts with a letter that's in that particular bucket. So this works. It's got a lock. You have to lock because you could have two processors trying to add to the same count at the same time. But it is also not very scalable implementation. So you've got this shared array, and so it doesn't really work very well on a shared memory, on a distributed memory kind of architecture. So now imagine you want to do the same thing in distributed memory. Why would you want to do this? Why not? It seems like you're making your life more difficult. Well, the answer is because I know Jim talked about these different architectures. It's really hard to build and to buy a machine that has a huge amount of distributed memory. So imagine now that your hash table is a terabyte, okay, and you can't, or maybe even 10 terabytes, and you can't fit that much memory into a shared memory system. So what you want to do this in a distributed memory system. So now you take the array and you distribute it out over, say, Hopper, which is a machine that you'll be using later in the semester for the homework assignments, and and now each processor still has a substream that it's working on, and it's going to just send either the particular word, or let's say that just all it has to do is send a kind of a +1 message to to the appropriate processor that owns the corresponding bucket. So obviously we have more than 26 buckets at this point, and then that processor receives it. So here's the problem, okay? How does this other processor know when to say receive, right? So you know when to say send, the processor that's sending. Apologies for anthropomorphizing parallelism in processors, but anyway, so you've got the processor there, and it sees a key that says it starts with, say, the letter D, and it sends it to the processor that owns the D count, but the processor that owns the D count doesn't there's no way for it to know when a D message is coming in for it to count. And so that's the complication with trying to write this kind of an irregular program with irregular kind of random updates across the machine in a message passing send-receive model. There are ways you can do it in MPI, and depending on exactly what your problem looks like, presumably you're not actually just counting the number of words that start with a particular letter. There's different tricks, algorithmic tricks and so on that you might use. But that's the kind of problem that motivates this class of languages. So to kind of go back and compare, the two programming models that you've seen before, you've seen shared memory. It's very convenient. People like it because it tends to be easier to take sequential code that they've written and turn it into parallel code. You don't have to often completely rethink your data structures. You can use the data structures, and you have to worry about synchronization. You have to worry about locking when you're going to lock them, and so on. But you can. It's usually a little bit easier than completely chopping up everything, which is what you have to do in message passing. So sometimes you can just do it by annotating loops. This is kind of the idea, the original idea behind OpenMP. In practice, when people write very highly optimized OpenMP code, and you'll learn about that, I think, in the next homework assignment, you may find that that's not the only thing you need to do, but it does depend on how difficult your problem is and how well the OpenMP compiler can understand what you're trying to do and then optimize it. Disadvantages: you have no locality control, right? You take your data structures and you just say this is a data structure. It's going to be shared by all the processors. There are variations of OpenMP that give you some kind of affinity or locality control, but that's not really in the model. It doesn't really scale very well. You can't buy very large-scale machines that do this, at least not at the same scale as a distributed memory machines. You can't buy a petaflop shared memory machine, for example, and you do have problems with race conditions. Now, on the other hand, in message passing, things are very rigid, they're very structured, and the advantage is that it's very scalable. You do have to worry about the scalability of your MPI implementation, and that's something that people still work on today. When you get to the point that you have a million cores in a system, if you have every one of those processor cores owns a little data structure that says, here are all the outgoing messages that go to the other 999,999 processors, you tend to chew up a lot of memory that way. So there's some scalability issues, but basically the programming model itself is very scalable because it is the programmer's problem to chop up their data structures into pieces. And the idea is most of the work is independent. That is, most of the work doesn't involve communication, so you work locally and every once in a while you communicate. Disadvantage, you really typically can't do this but without going back and rethinking your application. It's not just, here's my serial code, let me just sit down for an afternoon and figure out how I'm going to modify it a little bit to make it run in a message passing model. Lots of tedious pack and unpack code. I always like to tell the story of one of my graduate students who, and this was about 15 years ago, who had been writing a lot of really great parallel code for very irregular problems, by the way. Was doing symbolic computation, and symbolic computation has a lot of linked data structures, and you're shipping these things like polynomials around the system, which are represented as linked data structures. And he came in one day and said, I'm really tired of writing pack and unpack code. I don't want to do this anymore. I want to think about something else. He's doing more database kind of stuff these days. But anyway, did a lot of this kind of work, and it's not like it's hard, right? This is not rocket science to write code that takes a tree or a linked list and puts it into a contiguous chunk of memory and then ships it off to another processor and unpacks it on the other side. Really easy to get it wrong, though, because you've lost all the information about what that data structure was. And if there's an error in that pack or unpack code, sometimes you don't find it for a really long time. And then this problem that I tried to motivate with the histogram example, which is you don't know when to say receive sometimes. Now, it's not a problem in some applications, but in the histogram example it is. So PGAS languages, the idea of these is to fit somewhere in between shared memory and message passing. So we have the idea of a global address space, and this is our cartoon of what a partition global address space language looks like. The idea of a global address space is it's very much like shared memory. We don't use the word shared memory here because at the hardware level in these languages, we're not requiring that cache lines move around automatically under control of the hardware. That if you are not used to thinking about hardware, if you're more coming from the application side, the issue is that if you don't move things around and you touch a variable multiple times, you say, let's say you've got a big array A and you say A sub I and then A sub I again, and later in the code A sub I a third time, that you have to assume in a partition global address space model that if A sub I was expensive to get to the first time, that is far away in the system, it will be far away every time you access it. Whereas if hardware is involved, it might move it for you and say, oh, you access this, I think you might access it again. So it's your job to make copies of things if you want them to be fast the next time. So it's a global address space, so you can name anything in the system, and what that means fundamentally is that you have the ability to read and write memory anywhere in the system. So in the histogram example, you can go and write to a remote bucket of that, a remote array entry to increment it. Still have to worry about synchronization, by the way, but we have the ability to do that without asking the program on the other side to say receive. So the program isn't involved, we're just going to write, we're going to directly access the memory. So that's what a global address space gives us. What partitioning gives us is the ability to control locality. So unlike shared memory models like OpenMP, we're going to be able to say this array should be spread out in the following way in memory, or this tree is supposed to be chopped up in the following way, where this subtree lives on this processor and this subtree lives on this processor, and so on. So here's our cartoon. We have a set of P processors as in MPI. So you have, in the languages at least that we'll start with, that I'll talk about today, you use what's called a single program multiple data, or SPMD programming model. And what that means is that there's a static amount of parallelism, and it's exactly how much parallelism there is in the hardware. So you say I've got P processors, actually N processors in this case, and each one of them is going to have a chunk of memory. So, and there's some private part of the memory space, and there's some shared part of the memory space, which is the yellow part. So if you have, in this case, a linked list that's represented up here in shared memory, each node of the linked list can live on a different processor, but any one of these processors can walk down that linked list, okay? So it can do that by just dereferencing the pointers. These things are called global pointers, and if you look carefully, you'll see that some of the pointers here are fat, and some of them are skinny. The skinny ones are the ones that just point inside of my own piece of the address space, even if it's in the shared part of the address space. So there are things that are there are things that are in that are global, and a global pointer is really the important thing to understand. That's a pointer that can point anywhere in the system. And then there are local pointers, and local pointers only point within your local memory. Feel free to stop and ask questions at any point. Okay, so there's a few languages. I'll talk mostly about UPC today. You'll do a homework assignment using UPC. There is a Fortran-based language called Co-array Fortran. There's a new dialect of it called Fortran 2000, Co-array Fortran 2000, I believe. There's a version that we worked on a number of years ago at Berkeley called Titanium that is, and there's some newer languages that I'll say something about at the end, including one based on Python that Michael is working on, PyGas. And but these all have a kind of static model of parallelism, that is this idea that there's a fixed number of processors. By the way, whether each one of these corresponds to a single multi-core node in one of your architectures or belongs to a single core is something that you can kind of decide when you're writing the program. But there's other languages that are based on this PGAS idea of the address space that have different kinds of parallelism models. So X10, Chapel, and Fortran have much more dynamic threading models. And so I won't say a lot more about them, but it will just kind of point you to the fact that there are other languages like that exist. So a little bit kind of more about the motivation for these languages. If you look at the class of machines, and I think Jim showed this graph, or one that was similar to it, that looked at the kinds of machines that are on the top 500 list. And I've color-coded this a little bit differently. So we've got our SIMD machines up there. These are machines like the connection machine CM2 and the MassPar machines with thousands of little tiny processors. And then there were and vector machines, which are the single processor machines. The orange was up here that are no longer in existence today. And then there's the, so this is the top 500 list, which I think you have seen. And there's message passing machines, MPPs, and clusters in here, which are not quite as customized, but also basically versions of massively parallel machines. And if you look at how these things were programmed, well, first just a comment about there's a bunch more industrial machines on this list than there used to be when the list first came out, so there are a lot of applications in industry of high-performance computing. But if you look at how these machines were programmed, these vector machines and the shared memory machines were programmed basically by annotating serial programs. So an easy programming model closer to the shared memory model that I used. The vector machines were actually even simpler. You really could get away with basically annotating loops. Sometimes you had to go back and understand what the compiler was doing with your code and fix it, but it was a pretty easy programming model for people to understand and use. Then, and it was fairly easy to get from a serial program to a vectorized program. When we got to these MPPs and clusters and constellations and so on that had a network in between them, did not have shared memory, then people had to completely rethink their algorithms and their software to chop them up into a message passing kind of program. So one more kind of view of this, so that says that there's different kinds of machines in which you might want message passing versus shared memory. The idea of PGAS is to allow you to run in either kind of machine and still get good performance. And why does this come up in application domains? If you think about what most scientific computing applications look like, and Jim will be talking more, I know, next week about where parallelism comes from in a lot of these scientific problems, but he said a little bit about it already. Basically what you're doing in a lot of physical simulations is you're taking some domain, you're chopping it up into pieces, you're giving each processor a piece of it to work on, and a lot of the computation happens within that local chunk of work. So if you're simulating climate change on the globe, you chop up the globe, and each processor has a piece of it, and a lot of the work is done within that chunk. That's not to say there isn't important communication that happens between them, but a lot of times there are long phases of computation in which you don't have to do communication. And because you can kind of divide up the world this way, whatever world it is, whether you're doing a crash simulation on trucks or doing a simulation of the fluid flow in the body, you can divide the domain up into pieces, you compute on each one piece, you exchange some information between the other pieces, and you repeat. On a global address space model, you kind of start computing and you grab whatever you need whenever you need it, and you keep computing. And this comes up in practice where people really like these global address-based languages are where you're manipulating very large, irregular data structures. So think kind of big data graph analytics problems, looking at, say, graphs that come up in I think these are both some kind of web connectivity graph, so something like that, where the graph is so big that you can't fit it into a single shared memory machine, but you want to do some kind of complicated algorithm over it. So it's a much less regular graph than the kind of graphs that you'll see that come up from physical simulations. Okay, so now onto something more concrete, a little bit of a tutorial on UPC, and I will try to do this. Let's see, we'll go through some details at the beginning, and then there are more slides online that you can go back and look at. I think when you get to the point of your homework assignment, you may want to come back and look at these, but just to warn you, there are a bunch of slides that are hidden, so you want to go and look at the hidden slides too, or you may. So let's see. A little bit of history. Maybe we don't need to go through the history. I'll say a little bit more about this at the end. But just one point I want to make is that UPC is not just a Berkeley project. There's an international community around it. Certainly within the U.S., there are a number of different companies that have UPC compilers. It's used in production and things like that. Okay, so what is we're going to start with the execution model and just talk about kind of what the parallelism looks like. And the parallelism, as I said before, is going to be the single program multiple data model, SPMD, and that's going to be very familiar to those of you who are, how many people have ever programmed in MPI already? Okay, so those of you who have programmed in MPI, this should look very familiar, and for those of you who haven't, you will do that in homework 3, right? Homework 3. Okay, so what does the UPC execution model look like? You have a number of threads that are fixed at the beginning of the program execution, and there's a variable you can access when you're writing the code called threads, capital threads, and that is, so if you're running on 1,000 processors, so you have 1,000 threads, one on each processor, inside the program you can ask how many threads are running, so you can do things based on that number of threads. You can ask for which thread the particular executing thread is. So for example, if you want only one of the threads to do something like print out the answer, you can say, if my thread is equal to 0, then go ahead and do something. And there's a barrier operation, which is a synchronization that says wait for all the threads to get to the same point in the execution. So this is very useful if, for example, you want to make sure you don't have any race conditions in your program and there's some particular communication you want to do. You want to wait for all the computation to finish, and then you do the communication, and then you wait for the computation. So if you have these phases that are also very common in MPI. These barriers would not necessarily be very useful in the histogram example, where you want to have kind of all these things happening asynchronously. You're going to use something else for that, like a lock, basically. And there's going to be a form of a parallel loop. It's not actually that critical to UPC, but it is a way in which you can kind of think of things at a little bit higher level. But mostly your parallelism comes from the fact that when you launch the main function, it is already running in parallel. So I like this single program, multiple data execution model because it forces you to always think about parallelism, right? So in an OpenMP model, you're going to say, well, here's some serial code. Here's a loop. I want to parallelize this loop. Go off and parallelize this loop. We're going to say, no, you think about parallelism from the beginning of the program to the end of the program, and if there's anything that you want to do that cannot be done in parallel, you better branch on my thread ID or something like that to make sure that only one thread executes that. A sort of slightly ugly part of UPC that comes up is what's called it comes up when we start worrying about laying out arrays, and the fact that C compilers and so on only can allow you to use arrays that have a constant, a compile time constant in a certain part of the array declaration. And so there's two different modes in which you can compile programs, what are called static threads mode and dynamic threads mode. So static threads mode says that threads is, you're going to tell it when you compile the program what threads is. I won't talk about this a lot more right now, but you should come back and look at it before you start the homework assignment because it is important. And if you don't understand it, come and talk to Michael or David. Okay. Hello world in UPC. What does this look like? Well, here's a hello world program in C. I realize not all of you are maybe very comfortable or write a lot of code in C, but I guess you are probably right now in your homework assignments. So there's some ugly stuff to do I/O. Here's the main function. It just says print, thread. This, says number says it is going to be which thread I am of the total number of threads, and then and then just the rest of the string there. So this is just a regular old C program. First rule of UPC is that any C program is a UPC program. So that's very important. Not necessarily a very interesting one, but nevertheless it is a UPC program. So we can take this, so this is already not quite a C program because it's using my threads and threads, and it has this include up here, although that's all actually still standard C. But we're going to use these two variables. So without these two variables down here and this stuff up here, it would have been a valid C program. But now we put them in, and we can now run this in parallel, and it does something slightly non-trivial, which is each thread prints out a different number of what the number that they're on. Now, there's some questions that you might have about how this behaves. Anybody wondering? So there's questions that sometimes people ask about, how are these print statements going to come out? Is it going to come out print, 1 by thread 0, then thread 1, and so on? No, there's no reason to believe that thread 0 is going to print first. And in fact, there's nothing really inherent in this program that says that the letters aren't going to get all scrambled together on the screen with different threads printing at the same time. That kind of depends on how well behaved your printf library is. But that's so we'll have to be a little bit more careful about that. Okay, a slightly different example. Have you used the pi example, the Dart's pi example so far in the lectures? I don't think so. Okay, so really simple example. We can call it a Monte Carlo calculation if we want to make it sound like it's more interesting. But what we're going to do is estimate the value of pi by throwing darts at a unit square, so a 1 by 1 square, and we're just going to look at. We're going to compute of course, the area of the square is r squared, which is 1 in a unit circle, and then the area of the circle is going to be pi over 4. So we're going to randomly throw darts and just compute random values of x and y between 0 and 1, and then for each of those values, determine whether or not it's in the red part or in the white part. And then we'll compute the ratio of the number of points that are inside to the total number of points, and that should give us that ratio then should satisfy this formula, and we'll use that. We'll multiply it times 4 and get pi. Any questions about the example? Okay, so here's a little bit of code for computing pi in this somewhat tedious way in UPC. We have some variables declared up here, and there's a little bit of junk. This is kind of familiar to those of you who are used to C, that says I want to get some input, which is the number of trials, or otherwise I'll use 100,000 as the number of trials. So it's not really very important code right now for the purposes of this discussion. This is just standard C code, and this is setting up a random number generators, a seed and a random number generator, so they can get good random numbers out. That's, by the way, something else that you might have to come back to if you were going to write a program that really was going to do a lot of do a lot of random number generation, because it's non-trivial to figure out how in a very large parallel machine you get good random number generators. But we won't worry about that right now. The main part is right here, which is this loop that says for I equals 0 to the number of trials, we're going to call a function called hit, and hit is going to basically compute a random value of x, compute a random value of y, figure out whether or not they're underneath the curve, and if so, return 1, if not, return 0, and we'll just accumulate the total number of things that are hits, use that to calculate pi, and print the number. So just a serial C program, once again, is also a UPC program. If we run this as a UPC program, it will have each processor computing its own value of pi. Each one of them will come up with a reasonable estimate of pi. The idea, of course, is the longer you run, the better your estimate of pi should be, based on just getting a better number of random samples. But it will work correctly, except for the fact that each one of them, in some arbitrary order, will print out a different estimate of pi. So what actually. The colors aren't too great here. Each thread is going to, in the parallel implementation, each thread is going to get its own copy of these variables up here, and its own copy of the input arguments. And this was the initialization, and then this is each thread is calling the hits function independently. Okay, there's a little bit of helper code. This there's some stuff that wasn't shown in the include slide, the includes in the previous slide, because it didn't fit on the slide. And here's the code for getting the random value of x and y and so on. But that's just there for reference. Okay, so we want to do something more interesting than that. We want all the processors to work together to compute the same value of pi. In order to do that, we need to understand a little bit more about this partition global address space and how it works. So normal C variables are going to be allocated in what's called the private part of the memory space. So the white part is private, so look over there. There's private and shared. There's local and global, and these two ideas are somewhat orthogonal in the sense that a local global is a question about a pointer, whether that pointer is local or global. Private and shared is about where the thing lives. So normal C variables are going to live in private space down here in UPC. And so if we declare a variable called mine that just has a regular old C declaration, it sits down here in the private space. On the other hand, if we put this special UPC annotation before a declaration called shared, so we have a shared variable ours, it goes up into the shared part of the space. And so there's only one of those, and it's shared by all the threads. If this has been declared, then all of the threads can actually access this variable ours. They have to be careful to not stomp on what the other threads are doing. And so there's something you need to understand if you try to start writing some UPC code, which is you can't put shared variables inside of what's inside a place of the program that has a dynamic lifetime. So what does that mean? If you have a function that you've declared, and that function is going to have dynamic lifetime. When it runs, it'll run for a certain while, and then it'll go away, right? So it doesn't exist, the instance of that function doesn't exist throughout the program, and so those variables cannot be declared inside a function. So why is that? Anybody have a good... Why does UPC not allow us to put shared variables inside of a dynamic lifetime sort of environment? Well, if this ours is sitting in a place that can come and go in time, and every processor, every thread is supposed to be able to see it, then you're executing along, and let's say you're in a function called make hours, and so one thread, or the threads even all together, they call make hours, and they have this hours thread, the hours variable, and then thread 0, which is the one where it happens to be sitting. it returns from that make hours function, and that variable goes away. And the others still believe that they have a name that they can access. They still have, they try to access this hours variable, and it doesn't exist anymore. And it's going to go and look at some arbitrary piece of memory. So, so these variables can only appear in some place that is static throughout the program execution. Now, for that reason, they may seem very limited. In fact, we rarely use them like a basic scalar variable like this in a UPC program, except for something like a constant, where we want everybody to see the same constant. Yes?
So will it be possible to, I mean, when there's a dynamic global variable, and we just distribute a message to different slaves to inform them to, I mean, delete their instance of that variable?
You could, but the problem is that what you're asking them to delete is a name, right? You're saying to get rid of that name, which is, they don't have a variable to get rid of. So if it was an object, you could say get rid of your object, but I have, let's say I'm thread 0, I have the object hours, and I could tell you, everybody erase your name hours because I'm going out of this code, and that variable is going away. But it's a little bit, awkward. But you will have to do that kind of thing when we get to the point of dynamically creating things. Okay. Yes.
So in the same vein, is there any sort of kind of thing in the spectrum between this is my variable and this is everybody's variable, kind of like an MPI communicator where only certain people are on a communicator?
Very good question. It is a topic of current debate within UPC. So there is a notion of what are called teams in UPC that are under development, and they haven't been put into there is a specification process, and there's a community around it. And so in the Berkeley UPC compiler, there is an idea of teams. It's not really been agreed on by everybody. But that particular issue that you brought up, which is, well, what does it mean if I declare an array and spread it out over a subset of the processors or whatever, and then some of them go away or the teams get rearranged? That's one of the problems. So from a communicator standpoint, as in MPI, which is a subset of the processors that can all work together to solve a problem, we do have that, and it's one of the active areas of research. Okay, any other questions about that example I should have asked? Okay, so let's see. So in this, we can now take this program and make it a parallel program, and we're going to have, and I'm calling this a shared memory style because we're going to just use these shared variables like, what do we have? We have trials, and hits. Hits is going to be our shared variable. So that's going to calculate all of the hits that all of the threads see together. And so here's a little shared memory program that does this. We first of all divide up the number of hits. So somehow we figure out either from the user's input or using the default or whatever. I guess here's using the user input how many trials each thread is supposed to do. So let's say you want to try it 100,000 times. Every thread is going to try a subset of them. And now they just run the code that looks like it did before. It just says for I equals 0 up to my trials. My trials is the number that this particular thread is supposed to do. Just call the hits function, and if you get a 1 back, add it to the hits. Sorry, call the hit function and add it to the hits variable. And then when we're all done with that, we do a barrier, and then thread 0 puts out the answer for us. Okay, so what's the problem with this program? So there's a problem in this line, which I think is probably maybe so obvious that people don't want to say it. I don't know. So you have all these threads, and they're all incrementing this one hits variable together. Okay. There's a race condition right in this line. So this race condition is the way this statement actually executes, and you hopefully heard a little bit about this with pthreads or OpenMP, is that you read hits. A thread will read hits, add 1 to it and write hits back. So somewhere in the hardware, that's what's happening, or actually in the compiled code, that's what's happening. And so what happens is 2 threads both read hits. Let's say that hits is 32 at that point. So they both read 32. They both increment it. They get 33. They both write it back, and you get a 33. So one of the trials got thrown out because you should have gotten 34 when you only got 33. Okay, so we can fix this in a number of different ways. One of the ways that we can fix it is to is to put a lock around it, and that's something that UPC has. But we can also fix it by, there's kind of another performance problem with this, which is even if we put a lock around this, there's very little that's going to actually happen in parallel, because now the only computation is inside of this function, and there's not very much computation in there. And if you actually have them locking every time the increment hits, then they're all going to be waiting for the lock all the time. So we'll instead come up with a way, a data structure that will allow us to increment hits independently and then add the results together. Okay, so now we need to understand, in this particular formulation, there's a few different ways of doing this, but the first way we'll look at is by using an array of hits variables, and with each one of the threads being responsible for updating one of the elements of that array. So as I said, these shared variables like hours in the initial the original example I gave, or hits in the previous one, are not very common to actually see in UPC code because of this problem that they create a bottleneck. So if you've got a million processors, they're all trying to update one variable, it's not a good situation, even if they've got locks to get the right answer. So for an array, what's much more common is we're going to use shared arrays. So a shared array is also going to be something that lives in the shared address space, but unlike a simple scalar variable like hours or hits, it's going to be spread out over all the processors. So here's a few different ways of declaring them. You could say shared int x of threads that says there's going to be one element per thread. So assuming that we have 4 threads in our system, and then this is what x looks like graphically, is that there's 4 elements, and there's 1 element on each one of the threads. So the first one is the one that's owned by thread 0. If we declare something as a two-dimensional array, 3 by threads, then we're going to actually get a chunk of memory, and it actually is useful in C and therefore in UPC to think of what these arrays look like in memory. And what this is going to happen is going to be laid out cyclically. So the first 4 elements will be spread out over the processors, and then you start again at the beginning and wrap it around cyclically. And then Z is a 3 by 3 array, so it's kind of a weird layout here, because what you'd get is the thread 0 owns the first element of the first row, and the second element of the second row, and the last element of the third row. And it's kind of a funny looking array, but there may be some reason that you want this. So you can think of this Y array as being logically one that's blocked by columns. That is, a thread 0 actually owns a column of the array. All the other threads do too. Question.
So for each thread, the allocated space in the case of Y3 threads is spread out in a cyclical manner. What if I want, for each thread, a contiguous space of, let's say, 5 ints? Great question, and about 2 or 3 slides later, I'll tell you how to do that. It's called blocked layouts in UPC. So yes, if we want a contiguous chunk, we can do that as well. Okay, so we can use this simple cyclic layout, though, to make our pi example a little bit better. So we can say, rather than having each one acts as a shared counter, we're going to make an array of counters. So here's our all hits array of threads. And by the way, this is one of these places where we do have to worry about the compiler complaining that threads is not known at compile time if we compile it in a dynamic mode. So you have to make sure you compile this the right way to say, I know what threads is, and tell it I'm going to run it on, say, 4 threads or 16 threads or whatever. And so then we go into our main function here. We've left a little bit of code out, and this all hits is shared by all the processors, but it's spread out over all of them. So actually, it gives us a couple things. One is that each one has its own to increment, so you don't have to worry about race conditions as long as everybody only deals with their own thread, their own element of the array. And secondly, that it'll be laid out in a way that's local to the thread. So thread 0 will own the 0th element, so as long as it accesses that one, everything will work out well in terms of the performance as well. So here's now everybody's running their trials, and they're calling the hit function, which hasn't changed at all, and they're then incrementing into all hits sub my thread. So they're just incrementing the one element that they own. So this actually works. This works just fine. Then there's a barrier because we want to make sure all the threads are done with this before thread 0 tries to print the answer. Otherwise, it might finish first and print out an answer that is incomplete by the others.
But now you have a problem, thread 0. Okay, so everybody's done, but the hits are now spread out in the array, so you need to go through the array and add up all the hits that are inside the array. And so thread 0 goes through and still there's the one overall hits variable, and it adds up all the hits from the others. So if you think about what's happening down in the machine level at this point, if you've got 4 processors that are actually at different places, each one they're connected by a network, then what thread 0 is doing is it's going off to get the value that's sitting in thread 1's memory, then the value in thread 2's memory, then the value in thread 3's memory, and adding those together. But it does get the right answer, and then it prints it out. So this part is a little slow. The rest of it actually should perform pretty well. Any questions about that? Okay, so to try another variation on this, we can look at other kinds of synchronization. And I talked a little bit about locks already, about barriers already, and mentioned that we do have locks in UPC. Just to tell you a little bit more about barriers. UPC was designed, there's always kind of a philosophy when you design a language, and the first part of the philosophy is that UPC should be consistent with C. What is C? C is a low-level systems programming language. Unless you talk to a hardware person, then they consider it a high-level language. But for most of us, it's a low-level systems programming language. It reflects what the hardware looks like. The hardware has a chunk of memory, so when you allocate a 3D array in C, it is really, you can think of it as being a big linear chunk of memory, and if you want to index it with 3 dimensions, that's your business, but it really is a linear chunk of memory. And so the same thing is going to happen here, and what we were worried about in designing the barrier construct is that barriers can be really slow if I've got 100,000 processors all trying to barrier together. So we actually created what's called a split phase barrier. And so there's a regular UPC barrier, which is the one that we've used, and there's a split phase barrier. So the idea with a split phase barrier is sometimes the pi example is not a great one, but sometimes there's work that has to be done before you can go through the barrier, and there's other work that doesn't depend on what the other processor is doing, or the other processors don't depend on it. So an example of this might be you've chopped up your physical domain into some regions. There's some stuff in the interior that has nothing to do with what the other processors are doing at this particular time, and there's stuff around the edges that they need to see. And so what you do is you say, let me compute the stuff around the edges first, then I'll do a UPC notify, which says I'm all done with my part of the computation, but then while you're waiting, you don't wait for them right away, you just notify them that you're ready to go through the barrier, and then you go off and compute your interior stuff, which you can sort of spend some useful time doing something while the others are finishing their work, and then you do a UPC wait. And the wait says, now I need to wait for all the others to complete. So in this way, you can get better overlap of the synchronization phase with the computation. Okay. Another thing that UPC had, and I would say this one's maybe not quite so successful, was we were worried about programmers getting confused by different barriers throughout the code. So if you have branches like this, and you have a barrier in here and a barrier in here, you can get mixed up and not have them lined up very well. And so we allow you to give names to barriers, so you can, and names are actually just integers, so you can say, but we usually, by a good programming practice, we give it a name, so we define a barrier 12, which is the merge barrier, and then when we have this barrier inside here, we call this the merge barrier, and that way, then the compiler actually will check runtime. Sorry, there will be a runtime check to make sure when you hit the barrier that you're actually hitting one with the matching label, and that could just be. It's probably especially useful when you have very large, complicated programs. We were hoping that would help us more with a compiler analysis. I can't say, and by the way, if you're particularly interested in the compiler analysis problem, this was done much more elegantly in Titanium, but also in a much more rigid way in which those things are built into the type system. But in UPC, it's a little bit loose. Okay, now in our, we had a barrier in our pi example, but it wasn't really what we needed. So going back to the original shared memory style, if we want to fix that instead by putting in locks, even though it's probably not going to scale very well, we still want to. We'll just see what locks look like. So locks in UPC are an opaque type, meaning that You don't get to see inside how they're implemented because the implementers of UPC may use different implementations on different machines. And locks have to be allocated before they're used. So like any other kind of dynamic memory, so you say UPC lock T is the type, and you're gonna call this lock alloc operation. And you can also have all the threads get together, because this is very common is a case where you have a lock and you want all of the threads to know about the name of that lock. And so you can call a global lock alloc, which is going to allocate a single lock and had a pointer. So I think I've reversed these two. But anyway, this one will give you a pointer back to the one thread that calls it, and this one is called together. All the threads call it together, and they all get back a pointer to the lock. So this is kind of like doing the second one followed by a broadcast of that lock so that everybody has a name of it. So why do they all need a name? Because if you're all going to protect some shared state, then you all need to agree on what the name of the lock is that you're using. So to use a lock, then you actually say lock and unlock before and after the critical region of the code that you're trying to protect. And then you should free them up. Good programming practice. You should free up your locks when you're done using them. Questions about locks? Okay. So these probably are familiar to those of you who've written code with locks, and and might look a little bit weird to those who are not used to this. But here's my Pi example now using locks. So first of all, I had to declare and allocate a lock. The all underscore, I should have mentioned this before, is a common programming style used in UPC to indicate this is a function that every thread has to call together. And so the all lock alloc is everybody calls it together, which is what's happening at this point in the code because it's not inside of a branch. So all the threads are calling that together. They all get back the name of the lock. And then when they're doing their hits independently, you locally will go through and compute my hits, and then before you update the hits variable, you acquire a lock, and then do the increment, and then release the lock. So so this is maybe not so much worse in terms of the performance than the version with the arrays. The problem with the array version is that at the very end, thread 0 had to run through sequentially and look at everybody else's value. In this case, sequentially, all these increments to hits are happening, but they're also being locked, and the computations being done remotely. So it's probably somewhat worse. But both of them are they have basically the same kind of problem. So can anybody suggest a better way of doing this that would avoid this bottleneck? What's that? Atomics might make it a little bit faster. Atomics in UPC, remote atomics, also an area of some debate. Everybody would like remote atomics, but the hardware vendors don't all agree on what set of atomics should be standard, and so it's a little bit hard to put it into the UPC language standard. But yes, if this is running on a shared memory machine, I don't know if you heard about atomics, but basically they're very fast hardware mechanisms for doing things kind of like a lock, or actually doing a fast increment that's guaranteed to not miss one of the values of the increment. So that's one way of doing it. The other is you could have a couple of, anybody else? Other ideas? Tree, right. So you could use a tree. I think you heard tricks with trees in last lecture. So yeah, you can get, thread 0 and thread 1 can get together, add their two values together, then thread 1 and thread 3 can get together and add the results of those, and so on. And there's going to be collective communication, which I think you didn't hear about in MPI yet, but you will hear about on Tuesday. And the UPC also has that idea of collective communication for doing the tree kind of computations. Okay, so to kind of summarize what we saw in the types of variables that were in this example, we saw private scalar variables. So scalar, right, are just non-array kind of variables. They're just simple integers or floating point numbers. So scalar variables, like it was my hits, and they sit down here in the private part of the space, and nobody should be able to get to them. Okay, that's sort of the idea in UPC. Type system's not so strong that you can guarantee that, but that's the idea. Is those private variables are there's a copy for each thread, and you don't get access to them from other threads. And then the stuff that's in the shared space, well, you've seen both hits, which was shared by everybody but sat on thread 0. By the way, all scalars that are declared as shared go on thread 0. So like in C, you may not like it, but you know what you're getting. And the hit lock also goes on thread 0 because you just declared it. I think it got mallocked there. And then the array was spread out over all of the threads, and so that was a shared array. The shared lock was right there. So, was it a question? No. Okay. Okay, so I mentioned that there are UPC collectives, and I'll say a little bit about these, but we're now getting to the point where probably there's enough for you to think about in terms of the programming model, and you'll see these kind of collective ideas again in MPI, so I'll just sort of touch on how these work. So there is a UPC, oh, that's probably the wrong version number, I need to fix that, but there is a document that describes the collectives. It has the usual kind of operations that you have when you're doing collective communication that you should have seen in the tricks with trees. So the idea of doing a broadcast, which you can do as a tree, so it doesn't take you order P steps to do a broadcast, it should take you log P steps to do a broadcast. What are reductions, so the opposite where you accumulate everything together in a tree, and a parallel prefix sum, which you saw some reasons why you might want to use that kind of also sometimes called a scan operator, and then scatter gather, which are more irregular sort of distributions of data across the machine in different ways. So you should look at that interface if you want to do something collectively. Now the collectives also get into kind of a part of UPC where you're writing in a style that is more common to MPI and therefore also could be written in MPI, whereas when you're writing in this sort of, when you're just directly accessing allocating pointers and accessing dereferencing pointers is what I'm trying to say, then you're doing something that's more irregular and probably is harder to write in MPI. There's a kind of nasty piece of the interface of the UPC collectives, which was there because, as with barriers, we were trying to make sure that these collectives weren't going to slow down the entire application when you're running on a big machine. And so we're trying to avoid over-synchronizing. The other complication is that we've got a shared memory space, and so when you're doing these collectives, trying to figure out exactly what is happening in the middle of the collective can be a little tricky. I'll give you an example of that, I think, in the next slide. But the basic idea is that data that you're in the collective may be read or written simultaneously by another thread. So when we taught UPC the first time in this class, I think I was actually teaching the class at that point, and it was probably about 8 years ago or something. And what we realized is that you really need a very small subset of the collectives for doing your assignment. So we built these things called the value-based collectives, and they're just for doing collectives on things like integers and floating point numbers. They're not doing collectives on arrays. So collectives on arrays are much more complicated. So here's Pi in what I call a data parallel style. So data parallel is if you have a program that only contains collective operations and very little else. There's no other communication, at least, other than the collectives, and then there's just local computation. That's pretty close to a data parallel style of a programming because you're really just doing everything in really a serial kind of mode. And so here's what the Pi example looks like in this style. And the important point is you're doing an all reduce. It is a value-based collective, so it's got an all of V. It is part of the Berkeley UPC extension, and so this value-based collectives. And so you're adding together my hits and accumulating all of my hits together into a single value that's going to live on processor 0. And that says that processor 0 is going to be the root of the collective. And the UPC add says we're going to do an add operation to combine all the results together. And the int says the values are int, so do integer addition. So, and so that's the way the code looks. Now, there's more of a spec. I won't read through this, but for reference, you can go back and look at all the different kinds of things that you can do in the UPC collectives. When you do more complicated collectives, as I mentioned before, there's this problem that you can have variables that are being read and written at the same time they're being used in a collective. And so the basic idea in UPC is to have something called synchronization flags. And the synchronization flags tell the compiler and the runtime system, but also the programmer and anybody reading the code, sort of what else could be going on at the same time as this collective. And so the example here is is where we've got some stuff going on in shared space, but imagine that when you're trying to collect together all of these results and put it into a single place, that at the same time, some other threads are accessing those variables. And so the sync flags will say things about what else is going on in parallel. So for example, the modes are saying that you are, that there's either that the collective cannot begin before or after before the read or the write of data when the first thread has entered the collective. So it says that basically you can't start anything until the first thread has gone in. All as the other extreme, and that says that the collective function may begin only after all of the threads are in the middle of the collective. So that just kind of gives you a sense of the two extremes. For the most part, you'll probably just use the default, which is a 0 on this. Okay, a little bit more about work distribution and parallelism. There is a parallel loop construct. What we've seen, we haven't got to blocking, which is important, array blocking, but it is tied up also with the idea of distribution. So we'll switch examples now, and we're going to switch to the example of adding up two arrays, just two simple vectors, and v1 and v2, and putting the result in a third vector called sum. So if we declare v1, v2, and sum all as shared arrays, they're all going to be cyclically laid out. And so in the main function, we can just say, well, if my thread is equal to I modulo threads, that means that I actually own that array, the array element, and therefore I should do the addition of v1 plus v2 and add it into that variable there. And so this is what's called an owner computes rule. It says that each thread is responsible for computing on the data that it owns, and the other threads are responsible for their own updates. And so this actually parallelizes pretty well, and it actually has reasonably good locality because each thread owns, the v sub I, v1 sub I, v2 sub I, and sum sub I that it is involved in computing on. And but it's such a common pattern that comes up in UPC that there's a special loop construct for expressing this, which is called a UPC for all. And so the UPC for all statement, it looks just like a usual for loop. It has an initialization, so something like I is equal to 0, and then a test, I is less than n, a loop, which is incrementing the loop, so I++, and then affinity. So that's the new thing, is this affinity statement. And the affinity expression, says something about which one of the threads should execute it. So in a UPC for all, every iteration will only be executed by one thread, whereas by default in UPC, every thread executes every iteration of a loop. Yes?
On the previous slide, could you just do, or how come you couldn't just do like sum of my thread equals v1 my thread plus v2 my thread? How come you need to do
the loop? Yeah. Because if n is much bigger than the number of threads, and n is bigger than threads, right. it'll get wrapped around again. Yeah. But you could do something a little bit better here, rather than, what's happening in this case is the threads are going through these loops, and they're mostly not doing anything because they're all saying, oh, I'm not the thread this time, so I'll go to the next iteration. They're not synchronized, so they're kind of they could be a little, out of phase in terms of when they're doing it, but nevertheless, they're, there's a bunch of loop overhead here that we should be able, anybody could get rid of by just saying, well, let's just start them all at my thread and have them increment by threads, and then everything will work out. So that's exactly what the UPC for all is supposed to get us to do. So here's technically what happens when you put one of these affinity statements in a UPC for all loop is it translates into exactly what we had in the previous slide, which is the loop as it is with a branch in the middle that says if I own the affinity, if I have affinity as determined by that affinity expression, then I'll execute the loop body, otherwise I'll ignore the loop body in this particular execution. So what can the affinity expression be? Well, it can be an integer. So for example, and if it is an integer, this affinity expression is calculated modulo threads to figure out if it's equal to my threads. And if it is equal to my threads, then only that thread will, then you'll execute the iteration, otherwise you'll ignore it. So if the affinity expression in the previous example is I, then it'll work just fine. Just the threads that own that particular index, kind of have all the array elements at that index, will end up executing executing that iteration. If you're running through something like a linked list, may not be such a clear pattern of which elements you own. So what you could do is have all the threads run through a linked list, and then say, and then put in the pointer to that node in the list as the affinity expression. And if that is something that's owned by my thread, then I would execute the loop body for that node of the linked list. But this is really kind of syntactic sugar for the branch that I had in the previous slide. But a compiler should do a better job of compiling it, namely what we talked about before, which is start with, for an integer expression, say I is equal to my thread as opposed to I is equal to 0. I is less than n is the condition, and then I plus equals threads will increment to the next place in which you have in which case you have an array element. And so this is rather than having all of the threads do this with a branch in the middle. So we can now do vector addition with the UPC for all, and it gets a little bit faster because we eliminate some of the loop overhead in a decent compiler, and it's also a little bit easier to read. It says UPC for all starts with 0, goes up to n, has an infinity value of I, and then just has the expression, the statement in there as before. Any questions about that? Okay, so now we finally get to the point where we have more interesting arrays to answer the question about blocking. So you can have arrays that are not cyclically distributed. You can have blocked distribution arrays. And why do you want something like that? Well, sum is not a great example because you don't actually care about which other elements are nearby you in the sum example, as long as you own the sum sub I, v1 sub I, and v2 sub I. As long as you have all three of those locations nearby you, you can compute quickly. But if you have a computation that needs to look to your left and look to your right, and you'll see a lot of that when you start talking about sources of parallelism, and may have seen it before in any kind of relaxation method, then this is a really bad layout, because what happens is every thread is going to be doing communication to look to the left and to look to the right. So in this, with this simple example, if we want to have a chunk of data that's all contiguous in the array, then what we do is we can put in this blocking factor. And if you can put a number in here, and we'll see an example of that next, but you can also put a star in here. And star basically says put in the biggest blocking factor that evenly divides the elements. The language is a little bit more complicated because you have to deal with the fact that sometimes there's an uneven number of elements in the array, but that's why you put in a star and let the compiler figure out what the right number of elements is. So if you've declared it this way, that's fine, but you better not put affinity, but put I in as your affinity expression down here, because now we have a set of elements in which, say, the first 100 elements are sitting with thread 0, the second 100 are sitting with thread 1, and so on. And now if you do that put the original affinity expression in here, it's going to be off doing the sums for things that it doesn't own, right? Thread 0 is going to say, oh, I don't own thread 1. I don't own element 1 or 2 or 3 or 4 when it does own those. And so you instead want to put an expression in here that says, if I own the thing that I'm going to compute on, fortunately v1, v2, and sum are all got the same layout, so they're all aligned in memory. Then if I own that element, then do the computation on it. So you take an address of the ampersand of the place that sum lives in memory, and that says if I own sum sub I is local to me, then go ahead and compute on it. Yes?
Would that work in the previous case also?
Yes, so this expression is more universal, more general than putting an I in there. If I always put in sum sub I, if I go and muck around with my layouts and decide, oh, I'm going to block it by 15, it'll still give you the right layout. And by the way, you get the right answer. If you put the wrong thing in the affinity expression, you just get bad performance.
So question here. So if we define n to 101, and then we still use block layout, and we only have 100 threads, what will the compiler do? Okay,
so if n is 101 and threads is 100, what the compiler will do is, in that particular case, is I believe that thread 0 will get 2 elements and everybody else will get 1 element. And so it'll get 0 and 1 and the others will get the smaller number. I have to actually look at the manual and exactly how that round off works. But I think that's what it does. It'll do something reasonable in that case. Yeah. Okay. So you can have more interesting kind of blocking factors. You can leave it out, which gives you the cyclic layout that we've seen. It just wraps the elements around. You can have a blocked layout, which is kind of maximum block size that evenly divides things. So that's a star. You can have B, a layout B, which says, if you put 4 in there, you get 4 chunks, 4 elements on each one of the threads, and it'll wrap around cyclically again. So if you have 101 elements and you have a 4, you're still going to have 1 left over, and so it'll get put back with the first thread, with whatever blocks it owns. So that's the way the blocks work. And then there's this kind of funny one that you have to think about, but is actually very common to use in practice, and it's called indefinite layout, which says, and I probably should take the numeral one out of there, all of the array is going to live on a single thread. Okay, that doesn't mean it's on thread 0. It lives on whatever thread, wherever it gets allocated. And this will be particularly common when we start doing dynamic allocation of arrays, and we want an array that sits up in the shared memory space, but it's all sitting on my piece of the shared memory space, and other threads can access it when they want. So I put it up in the shared memory space for that reason, but mostly I'm going to access it myself. Let's see. So the affinity of an array expression, you can go back and read that and see kind of where it ends up, but hopefully the natural thing happens, which is you figure out the block size, and it gets wrapped around, and then the affinity is what you would expect it to be. Yes?
But if we choose to do an indefinite layout for many things, how will the runtime, at runtime, how will it get decided? How does it get load balanced on multiple threads?
Right. So the load balancing is entirely up to you, right? Every thread has a certain program that it's running, and it's running the same copy of the main program. And if you have one thread that allocates a whole bunch of stuff inside of its own memory, that would be bad. So instead, each thread should allocate some stuff in its memory, and then it'll work. Okay, I'm going to skip some of the other array layout stuff because I think it's not so important. I want to make sure that we get a chance to talk about kind of the way real data structures actually get built in a lot of the more sophisticated applications. And whether you'll need this in your homework assignment, I'm not sure, but this is what you actually do is you use a dynamic allocation, which will be done with a UPC alloc or UPC all alloc, which is all the threads getting together to allocate something. And so this is going to allocate some chunk of memory, which you can then use as an array, and it's going to be distributed in some number of different ways. So here's there's a global alloc, which is putting something into the global memory, and you can say how many blocks, and then the block size and the number of bytes. This is not a collective, so it doesn't have an all underscore in it. It's got an alloc, but not an all underscore. And so each thread can call this independently. And the calling thread is going to get a contiguous chunk in the memory space that has this shape, that has this n bytes blocking factor, and they're going to be distributed around. Whereas in the UPC all alloc, which by the way is a more common way to do it, all the threads at the beginning of the program, so one of the ideas in the UPC is you set up your data structures, your big ones in advance. At the beginning of the program, all the threads get together and they allocate their data structures, and after that they may go kind of their own separate ways to do different kinds of computation on them at different points in time. So here's an all alloc, which is a collective alloc, which gives you the same kind of data structure, but they have to be called together, and all the threads get the same pointer. They all get a pointer to the beginning of that array, which lives on thread 0. And there's a free statement, too, to deallocate them. Yes?
What does number of blocks mean?
Number of blocks is so rather than just saying there's an array size, we're going to break the array size into the size of a block and the number of blocks. So if you multiply those two together, you get the total array size, n. Okay, but you're kind of combining in the type system. Number of blocks is the block size, and then n bytes. The number of bytes is the block size, and it's probably not a great name for that, is it? Because it should be in words. But anyway, I think, yeah, it should be in words. And this is the number of those things that you're going to have. So if you multiply these, right, when you multiply these two things together, you get the total array size. But it's going to be an array that's chopped into n bytes chunks.
So this blocks are distributed over different machines, and we don't know where they.
We know exactly where each one is. So that's one of the principles of UPC. You should always know exactly where everything is. So block 0 is on thread 0, block 1 is on thread 1, and so on. If you have more blocks than you have threads, they'll wrap around. Yeah. Good. Okay. So this got a little bit scrambled on my screen, but it looks okay in yours. Okay. So let's see, distributed, when you're actually doing distributed, non-trivial distributed data structures, and sometimes even arrays, like multidimensional arrays in C are not such great things because they're really just contiguous chunks of memory. And so we often use a different kind of a data structure. We call it directory structure. And this is just now programming style. This is not hard-coded into language, but just to give you an idea what a lot of the real data structures look like in more sophisticated UPC programs, especially if you have multidimensional arrays, is you will make what's called a directory. So a directory is a cyclically distributed array of exactly threads elements. Okay, so there's one per processor, and each one of those points to a chunk of data that's shared on the processor. Now, there's a PowerPoint problem here, which I couldn't squish this all into a slide. So this is our partition of our global address space, or the dashed lines. So you should think of them as being sort of straightened out here to make it look more like our original cartoon of a global address space. We have our cyclically distributed array, and each one has a chunk of the data structure that it needs to access. So so hopefully you could see how to declare and allocate this array. You can just make it a shared cyclic array. And then each thread can allocate a chunk of memory of whatever size inside of shared memory, so using the UPC alloc, and stick a pointer to it in its memory location, in its array location. And then through this directory system, you can get to any other chunk of the array in the system. One of the nice things about this data structure representation is that you can make it hierarchical. So if you have 10 million threads in the system and you've decided you don't want such a big array, you can just have an array of 10 things, and those 10 things will point to another directory that sits on 1/10 of the machine as a directory for that that million nodes, million threads or whatever. You can kind of do what you want with this. The other thing that's nice is this directory doesn't have to be a one-dimensional array like this. It's probably the easiest way to start out thinking about it. But let's say what I have, and this is very common in physical simulations, I have a three-dimensional array, which represents my 3D domain. And so what I do is I allocate a directory that is a 3D skeleton of the entire array. So it actually has 3 dimensions inside of that. And each one of the elements inside that 3D array points to a really big 3D array that actually controls the data. So there's a little bit of replicated stuff here. The directories are replicated in this case. And not cyclic actually, but they all have a copy of them, and they all have the same pointers that point to the same 4 big chunks of memory. Okay. Okay, I'm going to skip memory consistency because we could talk about it forever. But it's an interesting topic for those who like to talk about memory consistency. And I'm going to just talk a little bit about the performance of UPC. And I want to make sure you have time to talk about homework 1. So one thing to understand about UPC is it is run on top of what's called one-sided communication as opposed to a send-receive model. So you can actually run UPC on top of MPI, but the way at least the Berkeley compiler works, and there's a GCC version of UPC that's also uses the same GasNet runtime layer that was built here at Berkeley, is it's built on this one-sided communication model called GasNet, which stands for Global Address Space Networking Layer. And what is fundamentally in this is a put and get model as opposed to a send and receive model. So what's the difference? So in a put and get model, a put and get has an address and a data and some data that you're sending, whereas a two-sided send and receive in MPI has a message ID and some data. And so the difference is that on today's modern machines, and that includes InfiniBand clusters as well as Cray supercomputers, IBM supercomputers like Hopper or the new Blue Gene Q system, Sequoia, or even the GPU system at Cray, the biggest systems at Oak Ridge, the network interfaces are pretty smart, and so if one of these one-sided messages comes in and it has an address in it, it will take that. The network interface hardware will actually put that directly in memory. And so it is different, the mechanism is different than what's happening in message passing. In message passing, there's a message ID, and the information about where the data goes in memory is sitting in the receive operation in the program on the other side. So what all this says, and this is somewhat old data, this is latency of doing puts and gets versus doing ping pong, doing MPI operations. So how long does it take to get across the machine? And this says that generally the UPC stuff is faster. What about bandwidth? Well, bandwidth, eventually both of these will send big enough messages that you should be running at the bandwidth limit of the hardware. But for kind of modest sized messages, there's also an advantage of using the one-sided model because there's not as much overhead. And so this says the bandwidth, which is up, is good in GasNet rather than MPI. So does this matter in real applications? Well, here's one example of an FFT. You'll hear more about FFTs next week, but just to give you an idea, in a big FFT, in the middle of it, you have to do a big transpose where you're moving all the data around the system, and it tends to be a really bad thing to do on networks. And the idea is, using this kind of one-sided communication model, you can actually get, you can do better kind of overlap, better use of the network, and get better performance out of it. So this is on a BlueGene BlueGene P system running up to 32,000 cores. And let me just skip through there's a lower overhead, better overlap of communication, and you get better performance. There's a few different algorithms in here that I won't go into. And there are similar results on the Cray XT4, which was the predecessor to Hopper. Here's some results on another application, which is a QCD problem. So let me just mention, as I said before, there are a bunch of other languages, of these PGAS languages. And here's a summary of some of the performance results over a few different publications that have been done at Berkeley, both Berkeley Lab and Berkeley on the campus, looking at things like 3D FFTs. This is a gyrokinetics code. The MILC is the quantum chromodynamics code. Impact is a accelerator modeling code, and so on. You can see there's some speed ups there. But there's a fair amount of performance tuning work in all of these versions of the code. So you have to you won't necessarily get faster code the first time you write it in a language like UPC. So the last thing I want to mention is that there is this idea of one-sided communication can be used in a lot of other contexts. So GPU clusters, the Dirac cluster, which is at NERSC, or the Titan computer, which is at Oak Ridge, which is a huge Cray system that has GPUs in it. The CPU and the GPU have different memory spaces, and you can use these kinds of memput and memget ideas in the GPU space. So this is an active area of research, is how to take this kind of a programming model and apply it to that. If you have a system with solid-state disk, which is faster than a disk but slower than DRAM, can you use this kind of a global address space to go between those models as well? And I will just mention there is work running UPC on top of GPU clusters, and there's a little bit more specifics here, but I want to skip to the last slide on also a Python-based language. And just, whoops, that slide I actually did want to talk about. And just say that there's some things that you can think about as projects in the class if you want to, which is related to ongoing work. What am I showing here? Okay, that is there's a UPC++ kind of a language that's based on overloaded operators, and with GasNet, there's some names of people here at the lab or on the campus that are doing this. There's the kind of this should say PGAS idea for vertical memory partitioning, like an SSD, a solid-state disk. This PyGas idea that Michael is working on, hierarchical type systems to get this idea of teams to really work well in this kind of a language model, and then more dynamic runtime systems, which is some joint work with Rice, so Vivek Sarkar at Rice. And with that, I should probably stop, and I'll take questions, though, while you're setting up, if you want to. Or do you want to just use my laptop?
If you have
you
the
can do
slides,
that. Yeah, I think.
probably easier.
I think I crashed. Are there any questions? Let's see. There it is.
Awesome. Oh,
Got that?
yeah, sure. Awesome.
I'll take this.
Alrighty, can everyone hear me? Okay, so hopefully everyone started on homework 1. Okay, blank stares, that probably means you're already done. So I put up this graph of different ways of doing homework 1. So starting off at the bottom, you have the blue line, and it starts off at about 10% of peak, and it falls off to about 1% of peak. That's your naive approach. I think that's about 30 lines of code total in that source file, but it performs pretty poorly. We also, the red line, we give you a blocked line. We give you a simple blocked code. It saves about 10% of peak. Again, pretty poor. Using this technique called unroll and jam, and you can look that up online. Any kind of graduate compiler's course will talk about how to implement it in a compiler, but you can do the kind of manually yourself. It's very simple. That's the light green line. That's about 45 lines of code, and it performs significantly better. When you combine the unroll and jam technique with the blocked code, you run at about 30%. And on this machine, you have to use the SIMD instructions to get above 50%. So if you take that unroll and jam code, do a little bit more blocking, and manually SIMDitize it, you get up well above 60%, which is the GSI code I show up there. And then if you spend 6 months working on this to your entire career, you would end up with the AMD BLAS performance up there. But
But 267 students have been known to beat the vendor BLAS.
That's
a challenge for you.
That's definitely true. They have, and maybe at one point we kind of kiss up there, but not. We're definitely not beating them. So. I think the big thing that probably most of you are going to want to do after you get kind of the simple blocking and register reuse done is to use the SIMD intrinsics on Hopper. So we've given you kind of a short little list here of all the intrinsics that our code uses. There are definitely more, but I'll make the assertion that you just need to use these to get good performance. So not that many. And you'll have this slide, so you can look all of them up later. And just as a quick example, here's multiplying 2x2 matrices with the SIMD intrinsics. And in this case, we're using the load U, and the U means unaligned loads. So for those of you that remember like CS267-2-14-13 here, we have the notion of aligned versus unaligned memory accesses with SIMD on x86. So if you can't guarantee that every load will be to a 16-byte aligned boundary, and if that doesn't make sense, you can come see me in my office hours. You'll have to use the unaligned variants because your program will crash otherwise. But they run at about 60% of the performance of the aligned variants. But just to get started, this is a 2x2 matrix, and you remember the blocking techniques we talked earlier. So you can build your whole matrix multiply, say, out of your inner block will be a 2x2 SIMDitized kernel, and then you can go up to cache blocking and all the way up, and that should get you well above 40%, hopefully above 50%, and if you're lucky, somewhere in the 60-70% of peak. So any questions? Questions on that? Has anyone manually used the SIMD intrinsics so far? You guys doing? What's the performance looks like? Like, good?
Well, I'm probably being an idiot. Mine's slowed down.
Yeah, that's going to be a problem. But
By the way, not at all uncommon when you're writing parallel code either. It's
Yeah.
the thing that happens to get slow.
So it looks like one of the important things is to fetch everything up to SSE line stuff instead of trying to do it like in the inner loop. Is that right? Or does it matter?
You cannot use unaligned loads in the inner loop. So.
yeah, the unaligned loads are really going to hurt that AMD microarchitecture. It's less of an issue on the newer Intel ones. But yeah, what's up?
So the attribute align
Mm-hmm.
for GCC and ICC, is it the same? Do they both pay attention to it? I know GCC is paying attention
Okay.
to it, but I don't know if ICC.
So the question is the attribute aligned. So if you have a variable and you want it to be if you have a statically allocated variable, so not something that you call the memory allocator for, so either new or malloc, GCC has a handful of attributes that will tell the compiler to allocate it on an aligned boundary. So ICC attempts to kind of hold the GCC contract, right? Because so much code, people, at least on Unix systems, assume GCC. So yeah, it'll align. I think actually by default, everything that's statically allocated like that will be aligned. But if you want to be safe, you can put it there.
Assume that M128s are aligned?
Yes, yes. Well, hopefully those are register allocated, so yeah.
I mean, an array of M128s is one.
Okay, yeah, it should be aligned. All right.
Is there some number of SIMD registers, or can you just make as many as?
Architecturally, there's 16. So in the ISA, they specify 16. So there's this technique called register renaming that computers use. I don't know how many renamed registers there are on this. But if you go beyond a certain point and your performance really starts to fall off, you'll see what happens. You've run out. Any other questions? I guess these are some quick things too. If you use a -S, you'll be able to see the generated assembly. You'll want to see these add SD and mul SD. So that's for add SIMD double precision and multiply SIMD double precision. If you see those, letters in this big long listing of assembly, you're probably getting the right thing. If you see PD, that's for packed, the SIMD. SD is for scalar. I'm sorry, I kind of transposed that in my head. But you want to see the PDs in there. That's good. And there are other compilers on the system. If you're using intrinsics and all of that, GCC is going to do a good job. But if you're going to try to massage your code into a way that an auto vectorizer will work, I believe the Pascal, PGI, and Intel compilers probably have a stronger vectorization engine if that's a path you want to go down. Pascal's the old SGI compiler, right? That's pretty good.
Originally, yeah, I think it did come on.
Yeah, something like that. So that might be better. What's up?
Did you say there's a difference in performance between saying A equals A add B or A equals add B and C?
You mean the plus equals versus A equals A plus?
Yeah.
There shouldn't.
There shouldn't be,
Yeah.
but that doesn't.
Let's say we have the vector registers. Would it be faster to add to the same register or have one register add together two other registers?
It shouldn't matter. It shouldn't matter.
But exactly what code the compiler will generate and is not always obvious, but it should generate the same code for those two things.
What might be happening is you're actually using more registers, and stuff is getting bumped onto the stack rather than staying in registers. It might not be the actual add instruction, but it's simply the number of registers being used.
Well, it's just in the case I have a bunch of registers, I'm trying to add them all up together.
You need to do a reduction in the vector registers.
Yeah.
There's actually an intrinsic half add. I think it's H add or something like that. It's in SSE 3. It's not very fast, but you can take a look at it. Anything else? Alrighty, well, good luck. And I have office hours today, and Michael will have office hours on Monday, and then I'll have them on Tuesday again. And everyone is actually logged into NERSC. Let's just make sure that, okay, that's good.